Annenberg Media.
One of the most extraordinary moments in human history occurred when astronauts first set foot on the moon. And yet, on the surface of our own planet, there lie tracts of territory where no one has ever walked. Only a very small group of people has even glimpsed this place firsthand.
It's not too surprising that humans have not actually walked on the floor of the deep ocean when we consider the extreme conditions that exist in that environment. Here on the Earth's surface, we live in sunlight and warmth, but the deep sea floor is in absolute darkness, with temperatures close to freezing. A person standing on the floor of the open ocean would also be exposed to the tremendous weight of the overlying water. This column of water, which is over 3.5 kilometers high, exerts a pressure hundreds of times greater than atmospheric pressure here on Earth. A person my size, for example, would be exposed to a total force of about 9 million kilograms. That's about 100 times the weight of this entire ship. A force like that would instantly crush my body to a lump about the size of a soccer ball. But the fact that scientists don't actually walk on the floor of the deep ocean doesn't mean we know nothing about it. Using research submersibles, which are specially designed to withstand the tremendous pressures, scientists have examined portions of the deep ocean floor in person by peering through windows 1/2 meter in thickness. Each window is made of a single flawless quartz crystal and is mounted in a titanium metal pressure hull 1 meter thick. But most of what we know about this remote and alien environment has not been learned by personal observation. It's been obtained by using indirect techniques. The high technology of seafloor exploration has produced a wide variety of remote sampling tools and marine robots that act as the eyes and the ears and the hands of the scientists who study the deep ocean floor. Studying the ocean floor using these remote techniques has produced a vast wealth of information, and the more we learn about it, the more intriguing it seems. In fact, the deep sea floor has not only played a prominent role in the evolution of our planet, it remains the most tectonically vigorous region on Earth.
We call our world planet Earth. A more apt name might be planet Ocean, since the oceans cover more than 70% of the globe's surface. This vast amount of water probably grew from the condensation of volcanic steam and from the melting of ice in comets which struck the primeval Earth. From the beginning, the oceans have contained more than just water. Carbon dioxide, chlorine, and sulfur dioxide, which are volcanic gases, dissolve easily in water. Sodium, magnesium, and many other elements weathered from rocks on land continuously pour into the sea from the mouths of rivers. These chemicals make oceans salty. If the surface of Earth were completely level, an ocean would cover the entire planet. But the surface is made up of two contrasting materials. Light granitic rock floats high, forming the world's continents. The heavier basaltic rock tends to sink, forming the world's deep ocean basins. The oceans average between 3 and 4 kilometers deep. However, compared to the total diameter of Earth, the oceans are but a patchy film of liquid covering the surface. Scientists have identified several different regions of the seafloor. Most of us have had first-hand experience with the shallowest and most accessible area, the continental shelf. Every time we go wading in the ocean, we're walking at the landward edge of a continental shelf. Shelves cover 1/6 of Earth's surface, sloping gently down from shorelines at an angle of about 1/10 of a degree. Worldwide, shelves average 70 kilometers in width, but in some regions, notably the Pacific coast, shelves can be as narrow as 2 kilometers.
If we started at the beach and went towards the deep ocean, we would see first the continental shelf, and then usually there's a quite distinct break in slope, and it's suddenly steep. That's really the geologic edge of the continent. And so it's shallow at about 200 meters depth, though it varies from place to place. Suddenly it's steep, and then it drops all the way to 4 or 6 kilometers depth to the deep ocean. So it's a very tall scarp from the edge of the continental shelf to the deep ocean. That's called the continental slope. Then when you get to the base of the slope, there's a huge, long, shallow slope where all the debris that's coming off the continent is deposited. And so it's a very gradual slope. That's called the continental rise. If you were coming towards the continent, you'd slowly rise up it. And it's all the debris that's coming out of all the rivers and off of the slope by a lot of different processes all end up in a big pile, slowly getting thinner and finer as you go away from the base of the slope.
In many places, the continental shelves and slopes are furrowed by deep V-shaped valleys known as submarine canyons. Where the shelf is wide, as on the Atlantic coast of the United States, these canyons begin far out from shore near the outer edge of the shelf. On the narrow continental shelves of the Pacific coast, the heads of some canyons lie close to the surf zone.
They've been a mystery for a long time, why they're there and how they're cut so deep. And they're also very interesting because an awful lot of the sediment that comes off the continent and onto the ocean floor goes down those canyons and debauches onto the ocean floor, makes huge fans of sediment at the foot of the slope.
Beyond the continental rise lies what is quite literally the flattest region on Earth, the Abyssal Plain. This landscape is formed as layer upon layer of sediment settles on the ocean floor. This material, known as pelagic sediment, consists of organic as well as inorganic matter. Pelagic sedimentation is not restricted to the abyssal plain, but occurs throughout the oceans.
The pelagic sediments are made of the debris that falls out of the water column and it's like a snowfall that falls on top of all the topography. And they're made of the microscopic shells of organisms that are in the plankton, and also all the clay and dust that blows out to sea in the air and then falls down through or that is stirred up in the water. These sediments come down very gently and drape over the topography, so it saves all the mountains and hill structure, even though it softens them up, just like a snowfall would.
Farther out along the abyssal plain, the seafloor bedrock becomes shallower and the sedimentary cover becomes thinner, exposing lava hills, which are actually the tops of volcanoes. Thousands of these volcanoes are scattered across the deep ocean floor. The larger ones are called seamounts. In fact, underneath the veneer of sedimentary deposits, the entire surface of the sea floor is volcanic in origin, although few signs of any recent eruptions are visible, except at mid-ocean ridges. Ridges are broad, mountainous features rising some 2 kilometers high above the surrounding sea floor and stretching up to 1,500 kilometers wide. The ridges are connected in a single system, snaking across the undersea landscape from one ocean to another, winding around the globe like the seam on a baseball. Unlike the crest of a continental mountain belt, which usually consists of a series of tall peaks, the crest of a mid-ocean ridge is occupied by a cliff-rimmed valley extending along much of its length. The walls and floor of this valley are split by numerous fissures. It is in this fissured valley that the most frequent volcanic action occurs on the ocean floor in the form of undersea lava flows. This volcanic activity is the key to a phenomenon that long puzzled geologists. There is a great disparity between the age of the continental crust and that of the oceanic crust. The rock underlying the continents is as much as 4 billion years old, and yet the oldest rock found beneath the ocean dates back only about 200 million years.
The fact that there is no ocean crust on Earth older than 200 million years raises an intriguing question. Does this mean that oceans didn't exist on Earth during the preceding 4.4 billion years of Earth history? Clearly, this can't be true. Fossils of organisms that lived in the sea are found in rocks older than 200 million years on every continent on Earth. In fact, fossils of multicellular marine animals range in age back at least 670 million years. And evidence of colonial marine algae, called stromatolites, have been found in the oldest sedimentary rocks on Earth. Discovered in northwest Australia, these sedimentary rocks and the stromatolites they contain are definitely of marine origin and range in age between 2.8 and 3.5 billion years. If, then, oceans did exist throughout most of Earth history, what has happened to all of the old ocean crust?
Analysis of cores taken from submarine rock reveals that the seabed becomes steadily older with increasing distance from the mid-ocean ridges. This research indicates that the seafloor originates and grows outward from the ridges. Geologists call this process seafloor spreading. The fissures atop a mid-ocean ridge are conduits through which fresh lava emerges. The lava hardens, but soon the crust is pulled open, forming new fissures and allowing more lava to emerge. Repeated continuously over millions of years, this process forms new seafloor. As the seafloor is pulled away from the ridge, it becomes cooler and denser. Eventually, it becomes so cold and dense, it can sink back into the mantle against the edge of a nearby continent or smaller ocean basin. This sinking of oceanic crust, called subduction, explains the absence of very ancient seafloor. Quite simply, it disappears back into the Earth. Subduction begins at enormous underwater trenches, some of them several times deeper than the Grand Canyon. Because of the great depth, marine geologists have had to come up with a host of ingenious ways of exploring the deep sea floor.
The primary tool used by Earth scientists to study the ocean floor is a research vessel like this one, outfitted with a variety of oceanographic sampling instruments. Mounted on the stern of the vessel is this A-frame, which is a hydraulically movable rack used to lift and deploy the instruments. The oceanographic sampling instruments are tethered to the vessel with this steel cable wound around a revolving drum. Scientists can take a bite of sediment or rock from the ocean bottom using a sampling instrument like this camel grab. It takes sediment samples very quickly, but only of the upper few centimeters of ocean bottom. Oftentimes, an undisturbed sample of the deeper layers is required to examine variations in the accumulated sediment on the ocean bottom with time. This box corer takes an entire column of sediment, which later can be split open, and the individual layers analyzed like pages in a book. But marine geologists need more than physical samples to understand the seafloor. It's like trying to understand an entire city by only visiting certain buildings and street corners. By examining the shape and global distribution of submarine landforms and determining their rock composition as well, geologists have been able to link the processes which create these landforms with the formation of the ocean crust itself. Most topographic mapping techniques used in seafloor exploration are based on the principle of sound waves bounced off the sea bottom, a technique called echo sounding. First developed for the military detection of enemy submarines in the 1920s, echo sounding devices emit a pulse of sound toward the ocean bottom and record the amount of time it takes for that sound to bounce off the bottom and back to the device. By converting echo time into water depth, an echo sounding device draws a two-dimensional profile of the ocean floor beneath the research vessel. In recent years, however, marine geologists have employed more sophisticated acoustical techniques to map the topography of the seafloor. These robotically controlled imaging devices can map an area of the ocean floor tens of kilometers wide in a single pass. This three-dimensional view of the ocean bottom can be clearer, more detailed, and even more valuable than the view of the ocean floor from the window of a research submersible.
One such imaging device is currently being used to map the territorial waters of the United States. In 1983, the federal government expanded this region to include all terrain within 200 miles of American shores. The U.S. Geological Survey was assigned the task of mapping this enormous new acquisition for possible future development of resources. At the core of this effort is a sophisticated echo-sounding technology called Gloria. Gloria enables broad areas of the sea floor on either side of the ship to quickly be scanned, unlike traditional sonar, which only provides a profile of the sea floor directly beneath the ship. Gloria itself is towed behind the ship, trailing 200 meters away, some 50 meters beneath the surface.
Well, Gloria changed our impression of the seafloor by, at one time, letting us view the entire seafloor, rather than viewing small patches beneath the ship, many, many tracks going every which way, and trying to interpolate between those tracks. Now with Gloria, we can see the entire surface. We can see where the seamounts are, we can see exactly where the channels are, where the meanders are, we can see where the canyons are, the gullies. We know now the locations of all these features, down to very small scale features. In that respect, Gloria was a complete revelation.
To accurately map an area of ocean floor using Gloria technology requires very precise navigation. The longitudes and latitudes of specific sites are determined with the assistance of Earth-orbiting satellites in communication with the research vessel. This technique is termed GPS, the Global Positioning System.
Navigation is the most important of all the data we collect. If we can't locate the image, or a bit of the image, exactly where it is on the surface of the seafloor on a map, then we haven't really done our job. Someone must be able to go back, after identifying something on a Gloria mosaic, go back to that latitude and longitude and find that image piece on the seafloor. So we use global positioning, we use GPS navigation, and it is the one thing that we pay more attention to on board the ship and after the cruise than anything else. It's the cornerstone for everything we do.
At this stage, however, there is still no image to look at. The Gloria data exists only as digitized bits of information in a computer, which must be processed and enhanced to create images showing the topography of the sea floor.
Over here.
Ultimately, other valuable information will come from Gloria work. Depths may be accurately determined for locations far away from the research vessel, and using characteristics of reflected sonic energy, it may even be possible to determine the type of material making up the seabed.
All right, the last one.
The individual images are pieced together to create a large mosaic view of the sea
Okay,
floor.
the tracks line up.
On an overlay placed across the mosaic, the geologists trace the important features which will assist them in making a final map. This overlay will also help in describing the geology of this newly explored undersea terrain. The atlas, compiled from Gloria's maps and images, is expected to have many applications.
The people that are interested in Gloria data vary from oil company geologists that want to know either where features are, the geometry of certain features, which we can provide them. Academic scientists want to know possibly an area that they're interested in. If we've imaged that area, they know now where to focus all their energy and all their money to look at the process that they happen to be interested in. The military, I'm certain, is interested in Gloria data. It's like any base map. It's a reconnaissance of the seafloor, so it provides the basis for beginning to understand everything that's there.
Some researchers are trying to understand where valuable geological resources are located on the sea floor. In a world of diminishing raw materials, the hope of exploiting the oceans for their resources has persisted for decades. At present, the only geologic resources being tapped from the sea floor are oil and gas, which occur within the shallow continental shelves. But in recent years, exploration has revealed many other resources. At the mid-ocean ridges, for example, copper, zinc, iron, gold, and other metals are being actively deposited from hydrothermal vents. On the deep sea floor, nodules of valuable manganese ore are scattered by the millions.
Manganese nodules are not composed purely of manganese. Only about 20% of a nodule contains manganese. Another 15% or so may contain iron with traces of cobalt, nickel, and other metals. But most of the nodules are made up of calcium carbonate and volcanic fragments. Where the manganese comes from has been a mystery, a problem for science. Two possibilities are that the manganese is extracted from waters washing off the continents or from exhalations through undersea hot springs on the mid-ocean ridges. The mid-ocean ridge origin is favored, but how the manganese is transferred through the water to very slowly accumulate as these nodules nucleating on the seafloor is in detail unknown.
But the technology required to harvest these undersea resources is formidable. And as with offshore oil drilling, there are serious environmental concerns.
Companies have experimented with dredging the ocean bottom for manganese nodules using giant suction devices. This has been successful enough to excite some commercial interest, for example, in Hawaiian waters. Harvesting ores off the mid-ocean ridge probably requires more care and is prohibitively expensive. Then there are environmental concerns. For example, if a mining operation were to ever start on a mid-ocean ridge, it could not help but destroy some of the fragile and spectacular ecosystem which makes its habitat there.
In addition to its economic applications, the use of sonar technology has helped scientists answer some profound questions about the nature and growth of the sea floor. For example, mapping shows how the positions of mid-ocean ridges change over time, and how the structures of ridges vary with different rates of spreading. Despite the usefulness of indirect means of studying the seafloor, more direct observations must sometimes be made. Samples are dredged to examine the makeup of the seabed, and cameras, operated by remote control, are sent to the bottom of the ocean.
You can imagine trying to take a picture is really hard because it's pitch black, and so you have to have the lighting. You have to bring your own lighting and turn it on and off. Then some of the more glamorous ways to study the ocean floor are to actually go in a small submarine. I've taken 12 dives to the deep ocean. It's like going to Mars. It's so different. But that's very frustrating too. It's like trying to do geology in a Jeep at midnight with dirty windows with your headlights without ever being able to get out of the Jeep. It's very, very frustrating business. It's lucky for us that the oceanic crust and the processes in the ocean are relatively simple compared to the land, or we would never figure it out at all.
But even with these limitations, submersibles and remote cameras have provided a wealth of information about the seafloor. Unique life forms thrive in the ocean environment, from the deep sea floor to the shallow continental shelves. Many organisms live suspended in the water throughout most or all of their lives. Others inhabit the ocean floor, burrowing into its soft sediment or scurrying across the silty bottom. Life has been found in many unexpected places. One of the most spectacular discoveries occurred when submersibles first explored the active volcanic region atop the mid-ocean ridges.
The most exciting adventure that we've had in the submarine, Alvin, was the discovery and exploration of the hot vents on the seafloor. They range from just a little bit warm to outrageously hot, 350 degrees centigrade. You know, ordinarily water would boil at 100 degrees centigrade, but the pressure's so high there that it doesn't boil, but it comes out extremely hot. When it's a little bit cooler, there are lots of strange animals that live around there that have never been seen anywhere else, including really long tube worms with bright red flesh at the end. There are crabs running all around, eating everything else. Giant clams like this with red flesh. All those animals are living on the chemical energy that's in the water of the vents. They have special bacteria that use the hydrogen sulfide. That's gas that poisons us if we get a tiny whiff. And they're using it for its chemical energy and passing that down the food chain. So it's a totally different ecological situation than we're used to It's so exciting to see a living thing in such an alien environment. They're really bizarre, really bizarre.
These weird and wondrous denizens of the deep are the only examples of life which get their entire supply of energy and warmth from the interior of the Earth itself. They live kilometers beneath the ocean's surface in a world as alien as any encountered in outer space.
The vast commitment of people and technology focused on understanding the seafloor is driven by two fundamental human motives. On one hand is our curiosity about the functioning of nature. The geology of the seafloor holds the answers to many vexing questions about the Earth and its history. What is the origin of the atmosphere and hydrosphere? How and why do the tectonic plates move? And how are the Earth's vast deposits of valuable resources, such as metallic ores and petroleum, actually formed? The geology of the seafloor holds the answers to these questions and provides unexpected intellectual dividends as well, such as the fantastic discovery of a self-contained ecology associated with deep-sea hydrothermal vents. On the other hand, we're compelled by the economic and political and environmental realities brought on by our industrial global civilization. And it's here that our scientific curiosity converges with more immediate human needs. For example, understanding the geologic origin of oil and gas and metal ores improves our ability to find and develop these resources in marine environments. This ability is increasingly important as our continental supplies are depleted. The seafloor also plays a vital function in determining global climate, and understanding its function helps us to better address such environmental problems as the greenhouse effect, changing global climate, and rising sea level. The seafloor makes up over 2/3 of the Earth's surface, and until recently, its vast submerged landscape remained virtually unknown. But now, as we begin to know and understand this strange, dark world, we're learning new facts about the way our planet behaves and discovering new opportunities to improve the future of all humankind.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.